Motion of a Falling Object, Lab 2 by Audrey Munger. In this lab, we are exploring the motion of an object by considering the forces that act on the object as it falls, like drag force and gravitational force. I used a bouncy ball. By uploading a video of myself dropping the ball on Tracker, I was able to compare an observational model of position versus time to two computational models, one with only gravitational force and one with gravitational and drag forces. The main result we will see in this lab is that the computational model including the drag force will be a better representation of the observed motion from Tracker. This lab focuses on the fundamental physics principles of Newton's second law, gravitational force, and drag force. Newton's second law says that acceleration of an object is equal to the net force on the object divided by the mass of the object. It is also seen as part of the velocity update and position update formulas. Drag force is a force that is seen when a solid object moves through a fluid, like air, that opposes its motion. Gravitational force is an attractive force that moves objects towards each other. On Earth, this causes objects to move towards the ground and is equal to 9.8 meters per second squared. In this lab, I dropped a bouncy ball, which was my system, and the surroundings included the air, chairs, camera, windows, walls, and so on. I uploaded my video to Tracker to make a position versus time graph of the ball's fall. The ball was tracked at equal time intervals for 18 frames. The change in position increases between each time interval, clearly showing that the speed was increasing towards the ground. The first computational model, the gravitational force only model, applies Newton's second law using the initial position of my bouncy ball, the velocity of the ball, and calculating in the gravitational force. Looking at the graph generated from the GlowScript code, we can see the position of the bouncy ball moves generally as expected, with its position decreasing at a faster rate as time increases. The second computational model, the gravitational and drag force model, is seen here. These two forces are in opposing directions. Looking at the GlowScript code, you can see that for this model, a non-zero value of b has been added, which is used to calculate the drag force. The position versus time graph generated by GlowScript has the same general shape as the previous model. However, according to Newton's second law, this one should be decreasing slightly slower because of the drag force working against the gravitational force. I took the data from Tracker and created a position versus time graph in Google Sheets, comparing this observed model to the two computational models. We can see that they all have the same general shape, with position decreasing at a faster rate as time increases. The computational model without drag can be seen to have an overall change in position slightly larger than the model without drag. This is accurate to what we expect to see from the observational model, because drag slows down an object's falling motion. However, there could always be more error present from possible errors in tracking or errors in coding. The first discussion question asks, which model, if any, predicts a terminal velocity? Terminal velocity is the constant velocity an object reaches when the resistance medium it is falling through presents any further acceleration. This is most likely accounted for by the graph of drag and gravitational forces. The net force at terminal velocity is 0. The second discussion question asks, imagine if the bouncy ball was initially thrown downward. Would the terminal velocity in this case be different than if the object was dropped from rest? The terminal velocity would not be affected. Terminal velocity is based solely off the magnitude of the drag force being equal to the magnitude of the gravitational force. It is not affected by the initial velocity. The bouncy ball may reach its terminal velocity faster, but the value of the terminal velocity would not change in this case.